Hey guys, this is Mrs. Harbin, and this is Chapter 3, which is all about functions, and today we are looking at proper rational functions. Our biblical integration for this unit is the reminder that God creates seasons for all areas of His creation. Good times and bad, life and death, winter, spring, summer, and fall. These are just a few of God's cycles, and when we're looking at functions like periodic functions, we're going to see these cycles. And because of these cycles, we can make weather predictions. We can do all kinds of other predictions with stocks and safety, and this helps us to better take care of God's creation, and that includes the people that are in it. Our lesson objective for today is that you, the student, will identify proper rational functions in reduced form, thus identify horizontal and vertical asymptotes, domains, and ranges of, and graph reduced proper rational functions. So let's quickly review the functions we've learned about so far. First, we have a constant function, and that's our y equals a number, and it might look something like this if your function were y equals 3, for example. A linear function, that's going to give us an x term. So y equals x, that's our identity function. So let's go ahead and graph y equals x. Obviously, we can change the intercept, we can change the slope, but our y equals x function, our identity function, is going to look like this, just a straight line. Okay, a quadratic function, that's where we've got y equals x squared. We've got this x squared terminology in all of our quadratic functions, and the basic shape of a quadratic function is a parabola. It can be inverted, it can be moved up or down or translated horizontally, but it's going to be a parabola. And then our polynomial function can take a lot of different shapes depending on the term, the degree of the polynomial. And so I'm going to just draw an x cubed function here so we can see what our basic x cubed function looks like. And that is going to be something like this. Now those are just sketches. Hopefully you can see that last one that I did there. If not, follow my mouse. So those are some of the functions we've learned about so far. In this particular chapter, we've also looked at absolute value functions, which we know is always a v. So here's just the standard absolute value function, where y equals the absolute value of x. Again, we know that we can move that up or down, or we can shift it horizontally by putting numbers inside the absolute value bars and outside the absolute value bars. A piecewise function. There's all different kinds of piecewise functions, but it's made up of different pieces. Maybe you've got a piece here, followed by a piece here, and then a piece here, for example. Okay, that's a piecewise function. Periodic function is something that repeats, and periodic functions can have all different types of looks. We saw one in our book that looked like this. Okay, where that 1, 0, 1, 0 kept repeating. And then lastly, we looked at trig functions. Now, trig functions are very closely related to the unit circle, and I know this is difficult to read, but thankfully you already have the unit circle memorized. Right? Our sine function is an odd function, and it's based on our sine values of 1/2, root 2 over 2, root 3 over 2, and 1. And when we graph our trig functions, our x-axis is labeled not in integers, but in radians. So at 0 degrees, sine is 0. At pi over 2, sine is 1. Let's make this 1 up here, and negative 1. Okay, at pi, our sine is back to 0. And at 3 pi over 2, our sine is negative 1. At 2 pi, we're back to 0. Okay, and you can even see that our sine is 1/2 at pi over 6. But if we're just going to sketch that, making sure we hit those zeros, our graph is going to look like this, going this direction, and like this, going this direction. So do make sure that you hit those zeros there and those ones. Everything else is just kind of a sketch. I'm going to switch colors here for our cosine function. A cosine function, again, comes from the unit circle. But our cosine function is 1, root 3 over 2, root 2 over 2, 1/2, and 0. So our cosine function starts at 1, and at pi over 2, it's at 0. And then at pi, it's -1. And then at 3 pi over 2, it's back to 0. So forth and so on. And we're going to repeat that process over here. So our cosine function, again, this is not perfect, but we're going to make sure that we hit our zeros and our ones. Our cosine function is a type of periodic function that looks like this. Right, and then we have our tangent function. Our tangent function looks very different because tangent is sine over cosine. So wherever cosine is going to be 0, our tangent function is going to be undefined. And so at pi over 2, our tangent function is undefined. And at 3 pi over 2, our tangent function is undefined. And we'll do the same thing over here. We'll put a vertical asymptote there at the places where it's undefined. I messed that one up a little bit. I wasn't paying attention to my axis. Let's try that again. And let's put the asymptote in the right place. There we go. Negative pi over 2 and negative 3 pi over 2. All right, and then you can see our tangent function at pi over 4 is where it crosses the axis here at 1. So this is pi over 4, looks like. Oh, that's where it's 1. Sorry about that. Here we go. At 0 and at pi, there is our place where it crosses the axis. And then we've got 1 and -1 at pi over 4, so here, and -1 down here. And so it's going to look like this. Oh, that's a terrible sketch. But hopefully you get the idea. This is an odd function as well with those asymptotes there. So there they are, laid over one on top of the other. So that brings us to rational functions, and our topic for today is proper rational functions. So rational numbers, we know, are ratios of integers. Rational functions are ratios of polynomials. Our dictionary definition, if you will, for rational function is a function f of x such that f of x equals p of x over q of x, where p of x and q of x are polynomials. Q of x cannot be equal to 0 because then it would be undefined. So basically, it's a fraction with a polynomial on top and a polynomial on the bottom. The domain of a rational function can be found by excluding values where the denominator would be equal to 0. So what we're going to do is take the bottom of the denominator, and if we set that equal to 0, we know that the denominator or the domain can never have that value because that's undefined. If x plus 1 is equal to 0, then this whole function is undefined. So our domain cannot equal -1. Let's evaluate for x equals 0 and x equals 1. All right, for x equals 0, we get -5 over 1. And for x equals 1/2, we end up with 1/2 and -19/6. So our domain is all values of x except for x cannot be equal to -1 because then we would have an undefined function. Let's give the domain of g of x. Again, all we need to worry about is our denominator here. The denominator cannot be equal to 0. So let's find all the values of x that make it 0. So we're going to set that equal to 0. If it were factorable, we could easily find those numbers. This one is not factorable, but we can find the zeros using synthetic division. So we're going to take our x cubed minus 6x squared plus 11x minus 6. And using what we learned about c over d, let's try to divide this by 1. And that works. And we're left with a reduced polynomial of x squared minus 5x plus 6, which we can then factor into x minus 2 and x minus 3. And we now have three values of x. that cannot be in the domain because they would make the domain 0, which would give us an undefined function. So for x, domain is equal to all values of x except for 1, 2, and 3. A proper rational function is a function in which the degree of the numerator is less than the degree of the denominator. So we've got x to the fourth and x to the fifth. The numerator degree, fourth degree, is less than the denominator. That makes it a proper rational function. A reduced rational function is a rational function in which the numerator and denominator have no common factors. Think of this in terms of reducing a fraction. When we have 2 over 4, we know that we can reduce it because they have a common factor. Both of these numbers can be divided by 2. Both of these numbers can be divided by 2, which gives us 1/2. So you're already familiar with reducing rational numbers. Now we're just applying it to functions. Let's take a look at 1 over x plus 5 and how we would go about graphing that. First, we would find the vertical asymptotes. That's the places where x is undefined. That's going to be where we set x plus 5 equal to 0 and find the places where x is undefined. In this case, x is undefined at -5, so we would graph a vertical asymptote. Then we would find the intercepts. To find the x-intercepts, we set x equal to 0, and when we do that, we get 1/5. And to find, that gives us the y-intercepts when x is equal to 0. To find the x-intercepts, we set y equal to 0 and solve. And when we do that, we get no x-intercepts. If we were to try and solve this, if we have 0 equals 1 over x plus 5, we would have to multiply both sides by x plus 5. This is going to be kind of difficult to read. Well, 0 times x plus 5 is 0. And these would cancel, leaving us with 1. And 0 equals 1 is not a true statement, so there are no x-intercepts. Okay, after we've done that, we would plot more points if necessary. Since there's an asymptote at x equals -5, let's pick a point that's on both sides of that point. So we're going to try f of -6 and f of -4. And we get f of -6 is -1 and f of -4 equals 1. So we would add those points to our graph. And to determine our range, we get our range is y is not equal to 0. In a proper reduced rational function, there is a horizontal asymptote. The x-axis is always a horizontal asymptote for a proper rational function. And this is proper because the degree on top is less than the degree on bottom. And it's reduced also because there are no common factors. But a proper rational function has a horizontal asymptote at 0. Now, quick note, horizontal asymptote does not mean we can't cross it. A vertical asymptote is like a force field. You can't cross it. The horizontal asymptote just shows us where the tails are approaching. You could cross it and then come back over, but the tails are going to be approaching this horizontal asymptote, and there's always a horizontal asymptote for a proper rational function. We have a vertical asymptote at x equals -5, and that y equals 0, what we just said, is a horizontal asymptote. Vertical asymptotes occur at any x value that makes the denominator or a reduced rational function equal to 0. And horizontal asymptotes tell you what happens to the tails of the graph. So while you cannot cross a vertical asymptote, a horizontal asymptote you can cross, and it just tells you the behavior of the tails, what the tails are approaching. So let's try to graph this rational function. X plus 2 over x squared minus 3x plus 2. We know that this is a proper rational function because the degree on the numerator is less than the degree of the denominator. Let's go ahead and find the vertical asymptotes by setting our denominator equal to 0. We're then going to factor, and we find out that x equals 2 or x equals 1. Those are the two places that would give us an undefined function, so those two are vertical asymptotes. To find our intercepts, we set x equal to 0. To find our y-intercept, and to find our x-intercept, we would set our y equal to 0. In this case, we can also just take the numerator and say our numerator is equal to 0. Okay, because we have a variable up there, we can set that equal to 0